All right, guys, welcome back. I know it's been a while since I've done any kind of science or math videos. This would be the first of a mini series on transformations. A lot of the times, what I've noticed is that students who approach transformations of different functions get a little bit overwhelmed when they try to apply the entire transformation algorithm towards any kind of function. So we'll separate this into different functions. We'll start off with the transformation of radical functions. And so remember that the parent function of a radical function is y is equal to the root of x. And what I always find it really helps to do is to graph the original function using a table of values, and then apply the transformation algorithms to that parent function. Okay, so let's say we have y is equal to root x. I'm going to look for x inputs that give me easy readable y outputs. So 0, if I plug in, let's say, y is equal to the root of 0, well, that would just give me 0. And so my first point would be x at 0 is equal to y at 0, and I'd plot it over here. Now the second point, if I go y is equal to root 1, well, that's just going to equal 1, which again is an easy plottable point. So at x is equal to 1, I'm going to plot a y output of 1. Now, for these two values, 2 and 3, if I plug in y is equal to root 2, right, 2 as the input or the x, that'll give me something approximately 1.4, etc. And that's going to be really hard to approximate on this graph. So what I'm going to do is I'm going to skip that value for now, because that's not a very easy readable y output, 1.4, and then of course the rest would be just decimal points. And same with 3. If I input y is equal to root 3, that would give me several, it'd be like approximately 1.7, and then several decimal points after that. So that as well, I'm not going to put as a value, because it's not easy and readable. Now, 4, if I plug in y is equal to root 4, with an x input of 4, I'm going to get a value of 2. And that is an easy plottable point. So we're going to go x4, 1, 2, 3, 4. And at 4, that will be 2. And so the parent function, when I connect the dots, will look roughly something like this. And of course it would continue. Okay? So, with that as a reference, let's see what happens when we apply a transformation to the parent function. Now, let's say the instructions are to plot f at x, which, remember, f at x is just another way of saying y, is equal to negative root x minus 3 plus 4. And so what we're going to do here is draw this function over here onto this graph. Now, in order to do that, we need to recall the transformation algorithm, or the formula, for radical functions. So the transformation algorithm here is y is equal to a root b multiplied by x minus h plus k. Now the letters here, which I'm going to underline in blue, correspond to the transformations or changes that you're going to make to this parent function over here. And each letter has a specific way that it's going to do that. A refers to vertical transformations, where your point or your graph will be vertically compressed. Okay, and we're going to box this, and this will be for A. if the absolute value of A is less than 1. Okay, and you know what we'll do? We'll write this in a different color so that it's easier to see. So if it's less than 1, there'll be a vertical compression. By the same token, there'll be a vertical stretch if the absolute value is greater than 1. Furthermore, if the absolute value, or not the absolute value, but the A value is less than 0, which really just means it's a negative, then there's a reflection on the x-axis. And so what that means is, let's say I have my graph over here. Okay, and let's say I have a point like this, or not a point, but a graph. A reflection over the x means that I'm going to take all the points associated with the blue line and flip them over the x so that it looks like this. And so with our A value, you can determine if it's being vertically compressed, stretched, or reflected on the x-axis. Now for the B value, this refers to horizontal compressions if B is greater than 1. By the same token, if B is smaller than 1, then your graph will be stretched or horizontally stretched. If the B value is negative, or we could say less than 0, then there's a reflection on the y-axis. And what that means is that, let's say once again, we have our graph here. Okay. And let's pretend that my parent function, or one function, let's say that this is a radical function, so we'll make the parent function something like this. Let's say the B value is negative. Well, I would take all the points from the blue, and since this is the y-axis, I'm going to flip it over here, and it would look something like that. So this is reflection over the y-axis. It's important when it comes to the B, and I'm going to write this as a starred note underneath here, is that when it comes to the B value, the horizontal stretch / compressions occur by factors of 1 over B. So for example, if your B is equal to 3, then according to what we've written over here, when the B is greater than 1, you get a compression. Then your graph is going to be horizontally compressed by a factor of 1 over 3. And finally, the H and K pertain to what we call translations. The H corresponds to horizontal translations. And so that would determine whether the graph moves to the left if it's negative, or to the right if it's positive, if the H value is positive. And then the K represents vertical translations. So that one, again, similar to the horizontal, if it's negative, it moves down. And then if it's positive, it moves up. The other thing I want to mention is with the H, remember that we set the bracket to 0. So we always take, in fact, the opposite sign when deciding whether it shifts right or left. So for example, let's say you have x minus 3. Well, to isolate for x, you would actually set this to 0. So we would go x is equal to plus 3. And that comes from the fact that x minus 3 is equal to 0. If I solve for x, it goes on the other side. It becomes x equals 3. So when there's a minus, this x minus 3 over here would actually mean that it shifts to the right because, and let me write that a little bit better here, it shifts to the right because it's really a plus 3. By the same token, let's say I had the bracket x plus 4. Well, this is really x plus 4 is equal to 0. And so if I isolate for the x, well, that would be x, which means I bring the 4 over, it becomes negative 4. That'd be x is equal to negative 4. And so this over here, the x plus 4, would mean that it shifts left by 4 because it's minus 4. However, the K doesn't work that way. If it's minus, it goes down. If it's plus, it goes up. So now what we're going to do is, using all those translations and transformation bits from the main equation here, we're going to apply it to help us translate the graph in red to the function that is given right over here that has been highlighted and boxed in red as well. So the key thing is that we want to identify what is the A, the B, the H, and the K. So remember that the A is always going to be outside the bracket, and so when we look at this over here, the negative, that would be the A value. So I'm going to draw an arrow from there and write A. And because A is negative 1, remember that if it's negative, that means that there's going to be a reflection over the x. So somehow the graph is going to be flipped over this way. Now, other than that, the value is 1, so we're not going to have a stretch or a compression, so we can kind of move on from there. When we look at the b value, and the b value is going to be right beside the x underneath the root. In this case, there's nothing here. We just see like a 1. So we're going to assume that there is no horizontal stretch or compression. And because there's no negative, there isn't a reflection over the y-axis. So we can kind of leave that there. Now, so we're going to write b, no change, right? So it's just equal to 1. Now, the h value corresponds to whatever is subtracted or added from the x. In this case, that'd be minus 3. Now, remember what we said, that this here would be set to 0. So really, what we have is, we have x minus 3 equals 0, which then if we isolate for x, our h value would actually be plus 3. So we're going to go here and write h is equal to plus 3. And what that means is that the graph shifts to the right. And so every single point over here, the 0, the 1, the 4, that's going to shift 3 units this way. And when we actually apply it, you'll see what that means. And then, of course, we have the k value, which, again, we don't have to reverse the signs because that part of the function is not going to be set to 0. And so since it's positive 4, we're going to say that it moves up by 4 units, right? Or just by 4. So now we know that there's a reflection over the x. There's no change in terms of a horizontal compression or stretch. There is a horizontal translation or shift by 3, so shifts 3 units to the right, and it moves up by 4 units. So there's 2 ways that we could do this here once we have all this information. We can either take this and apply it directly to the graph above, or we can apply it to what we call the coordinate system. And so the way the coordinate system works is that we use 3 points from the parent function and apply these algorithms or these formulas. Algorithm is really just a fancy word for formula. Y prime, or we can even think about this as the new y, after you've made all the transformations and translations, is going to be equal to a, so the value of a from your transformation function, multiplied by y, which would be the old original value. So that would be these values over here, plus or minus k, depending on whether k is a negative or k is a positive. As well as for the x, this would be the old x value, meaning these in the parent function, is equal to x divided by b, whatever that b would be, plus or minus h, again depending if it is positive or negative. So when we go up to our original data set, we can see that when it comes to the parent function, f is equal to, or f at x is equal to root x. So I write that down here, f at x is equal to root x. We see that the useful points, so the 3 points that we're going to use here, are going to be 0, 1, and 4. So we're going to go x, 0, 1, and 4, and then the y values 0, 1, and then 2. And we're going to apply these formulas to each of these points, starting with the x. So for our first point, when x is equal to 0, we're going to go 0 divided by 1, because we said that there was no change in b, which really just means that it's a value of 1. We're going to go 0 divided by 1 plus, now our h value is 3. So we're going to go 0 plus 1, 0 divided by 1, which gives us 0, plus 3. That means that x prime, so the new x, is going to be 3. So our 0 is going to now turn into a positive 3. Now if we take the 1 and we do the same thing, we go x prime is equal to, it'll be 1 divided by 1, which was the b value, and then plus 3, which is the k value, or not the k, sorry, the h value. Then that gives us a value of 4. So I'm going to scratch that out and put 4. And then of course I'm going to do the same thing with the 4 value here, where we go, and we'll make this a little bigger so you can see, we're going to go x prime is equal to 1 over 1 plus, oh sorry, not 1 over 1, it'll be 4 over 1 because the x value is 4. So it's 4 over 1 plus 3, and then x prime is going to be 7. So now I erase these after I've done these translations, and the new points are going to be 3, 4, and 7. Now I'm going to do the same thing for the y primes with the new y values. I'm going to apply it to each of these values. We're going to use this algorithm or this formula here. So we said that a was -1. So I'm going to go right here. Y is equal to, so y prime, so this is the new y value. We're going to go -1 multiplied by 0 because this value is 0. And then plus or minus k. Now if we look back here, we said that k was 4, positive 4. So we're going to go -1 times 0 plus 4. And that's going to give us a new y value of 4. So the first one where it says 0, we're scratching it out and we're putting 4. Now for the 1, we're going to go y prime is equal to -1 times positive 1 plus 4. And that's going to give us a value of -1 times 1 is -1 plus 4 is -3, or plus 3, so that'll give us a value of plus 3. So now instead of putting 1, we're going to go 3. Okay. And then finally, this value over here too, we're going to go y is equal to y prime is equal to -1, and let me put that inside the bracket, should be inside. -1 multiplied by the old value of y, which is 2, added, of course, the translation, the vertical translation of positive 4, and a -1 times 2 is -2, and then plus 4 is going to be positive 2. Now using this new chart, we're going to apply these new points to the graph. Okay, and we did it slow the first time because this is the first example, but the next time we'll do it quicker, and you'll see that you'll be able to do these a lot more quickly and confidently as you get used to it. So apply new points to graph, and that would be the parent function, okay, or the parent graph. So now using our new chart here, we're going to graph this in blue. So we're going to go when x has a value of 3 over here, y will have a value of 4. So we'll go to 1, 2, 3, 4, and this is now the first point. When x has a value of 4, so 1 over, y has a value of 3. So starting at 4, we'll go 1, 2, 3, just like this. And then finally, when x has a value of 7, so we're going to move all the way to 7, 4, 5, 6, 7. Y has a value of 2. Something like this. Actually, well, sorry, we're going to graph that a little better. So it'll be something like this. So we got 4, 3, and 2. And then when we connect the dots, it looks something like that. Now you can see that it's facing the opposite way. So while this concaves up, the red function, right, you can see that it concaves this way. The blue graph concaves down, right? It goes like this. And the reason for that is because there's been a reflection over the x. Okay, so this thing has turned upside down or has gone this way. So it is slightly inverted, and it has to do with the reflection. Let's do another example applying the same transformation principle.